it starts from 0, or in some cases it starts from 1. Okay, you should keep in mind that these two sets are not equal. It is that some authors consider this set as the set of natural numbers, however someone else considers this as the set of natural numbers. So whatever be the case, no natural number is less than 0. All of them are greater than or equal to 0. If we follow this, and they are strictly greater than 0 if we follow this set. So that means there cannot be any such x. So no x that is in N satisfies the condition. So this set remains empty. There can be no element in this set. As such, it is an empty set. Now note this article N. I have not said the empty set. However, there is only one empty set and it can be proved, and we are going to prove that now. Okay, so you can take it as a lemma. There is only one empty set. Suppose we want to prove this. What shall we do? How shall we approach this problem? I mean, one way of doing it is to assume there are two empty sets. E1, let me call this E1. E stands for empty. E1 and E2. Okay. Now, what is my aim? My aim is to prove that E1 is equal to E2. That is, they are the same. That way I can prove that there is only one empty set. That if I consider two, I'm not saying different, okay. In mathematics, when you see this type of words, 2, 3, it is not assumed a priori that they are distinct. They may not be distinct. I mean, this may be two it's like someone having two different names. That does not change the person if you call him E1 or E2. So it's like that. It may be that a single set has two names. So we have to actually show that if both the sets are empty, then they are one and the same. Okay. So that means, let us write, we claim E1 is equal to E2. Okay, this is what we want to prove. Now, how do we prove this? If you recall from one of our previous videos on set theory, that E1 is equal to E2 if and only if E1 is a subset of E2 and E2 is a subset of E1. And this thing is called the principle of extensionality of sets, if you recall. And that time I told that this is a standard procedure for showing that two sets are equal. You show that this is the case and also this is the case. So that means we are to prove. So we are to prove E1 is a subset of E2 and I have run out of space, so I have to wrap this up. and I am continuing the proof from here. Okay, and E2 is also a subset of E1, right? Keep in mind that we don't really know what E1 and E2 are. The only thing we know is that both are empty. They don't have any elements. Now, that is, now how can these statements be written? What is the meaning of E1 being a subset of E2? It means that every element in E1 has to be in E2. Just remember one thing, while doing or thinking of mathematics, you don't try to think of the quantities or the objects in them as you like. Always go back to the definition and see precisely what is said in the definition. Only that has to be applied. Okay, if you try to, although the name is intuitive set theory, but I mean, we cannot do just about anything in the name of intuition. Okay, so the very definition of subset says that is we are required to prove E1 being a subset of E2 means X belongs to E1 implies X belongs to E2, and X belongs to E2 implies, you can also use a different name, Y belongs to E2 implies Y belongs to E1, so that it is clear that we are just simply considering the implication and nothing else. Okay, these need not be the same. Now we have to prove this one and this one. Now, okay, so these are implications, and when are implications true? We have already discussed this in mathematical logic. When either the hypothesis is true and the conclusion is true, or when the hypothesis is false, no matter what the conclusion is. The first case is straightforward, the hypothesis is true, you prove the conclusion is true. However, in the second case, when the hypothesis is false, the implication is vacuously true, it is automatically true, it is considered to be true, it's a convention, recall that. Okay, now in this case, what are the hypotheses? We have two implications. So the hypothesis says that in the first one, that X is an element in E1. However, according to our assumption, the sets E1 and E2 are empty. So can there be any element in E1? No. So that means here the hypothesis is false. Here also, since E2 is empty, the hypothesis is false. So that means this implication is true, and this implication likewise is true. In fact, vacuously true. Vacuously true, this is also vacuously true. Nevertheless, they are true. Okay, so that's what we have to show. That means we have finished the proof, and this is the end of the proof, which means that we must have, if E1 and E2 are both empty, then they must be equal. So there is only one empty set. Okay, there cannot be two different empty sets. There is only one empty set, and there is a symbol for denoting this. Now that we have established the uniqueness of empty sets, there is only one. We can now say the empty set. Okay. So there is only one empty set one empty set, and it is, or it's denoted by this. You write a 0 and strike it out, or sometimes we use the curly brackets which are used to write sets, but we don't write anything in between to denote the fact that the set has nothing. This, however, is an old usage and it is not frequently used. This one is used more often. I think this has fallen out of use. This one is no longer used. This symbol is used. It's called phi, which is not Greek phi. Okay, some people make this mistake. Greek phi is different from this symbol. This is the symbol for empty set. This is the Greek letter phi, but this is empty set. Okay. Now, having introduced empty sets, then we have the next type of sets is called a set having only one element. Is called a singleton set. If a set has only one element in it, then it is called a singleton set. For example, this is a singleton set. It has only one element and that element is 0. Okay. Then this is also a singleton set. We are writing it in set builder notation. Why is it a singleton set? You see what the set is. This is the set of all real numbers whose square is equal to 1. So there are, as we already know, there are two real numbers, -1 and 1, whose squares equal 1 among them, but there is an extra condition that it has to be greater than 0. So there is only one such number. So that means this set is nothing but this set. So it also has only one element, although it's not 0, it's 1. But it says it's another example of a singleton set. Okay. Then the next type of sets. Do you see one pattern? The types of sets, we have started with empty set, although we have shown some sets previously, but that is a different matter. Okay, that was shown mainly for the purpose of showing you the symbols that are reserved for those sets, special sets. Okay, so the starting is from empty set, then we increase the number of elements. At first there is nothing in the set, then we have one element. Then after that, of course, we cannot go on like sets having 2 elements, give them a name. Sets having 3 elements, give them a name. That does not get us anywhere. So we make the leap, okay, big leap, and we define a set having only finitely many elements is called a finite set. Okay, a set having only finitely many elements is called a finite set. For example, the empty set is finite because it has no elements, zero number of elements. Every singleton set is finite because each one of them has only one element. Then, for example, this set that we previously considered while discussing roster notation, the set of first 100 positive integers. This is also a finite set, although its size is much larger than these sets. Okay, so, the size can be anything, but it has to be a finite number. Okay, the set can have 1 million elements, 1 billion, trillion elements, still it's a finite set. And why are we stressing this? Because we have already encountered infinite sets. You see, the set of natural numbers, all those examples that we have just now discussed, they are examples of infinite sets. They don't have, you cannot say anything about their number of elements. Each one of them has infinitely many elements. So naturally, a set that is not finite is called infinite. A set which is not finite is called infinite, and examples we have already seen, many of them. Now, the number of elements in a finite set A is called its cardinality. Let me write here. Cardinality or cardinal number of the set, which is nothing but, for example, the cardinality of this set is 100. The number of elements that a set has, or in other words, its size or order, that is called cardinality.